Okay, so this is going to probably be the last section of this that I do. I feel like between all of these reviews, you guys are seeing a good scattering of problems. And anything that I didn't cover that you have a question about, you can always email me about that. So I'm just going to run through some more of these multiple choice and we'll see what we see here. Okay. So this number 48, which of the following statements about caffeine, whose formula is C8, H10, O2, and 4, which statement is not correct? So let's look through statement by statement. 4 molecules of caffeine have a mass of 776 grams. So we are going to look up here. We have a mass of 194 grams per mole. So we can definitely say that if we multiply this by 4, that is 776. All right. Caffeine contains 28.9%. I'm skipping the correct answer, by the way, just so we know this. Caffeine contains 28.9% nitrogen. So this question's a little more annoying because we have to break down each part of the caffeine molecule. So I'm going to run through and write the masses for each of these things down. So the mass of carbon is 12.01 times 8. That's going to be 96.08. Hydrogen is going to be 10. Oxygen is going to be 32. And nitrogen is going to be 56.04. Okay, now we're really only concerned about the nitrogen mass here, but I just, kind of wanted to remind you guys of how we solve these things out. So to figure out what the percent nitrogen is, we're going to take the mass of nitrogen, which is 56.04, divide it by the total mass, which is 194 grams per mole, and then multiply it by 100. Okay, so that's like 28.9% nitrogen by mass. Perfect, that's what it said in the question. 1 mole of caffeine has 6.022 times 10 to the 24 hydrogen atoms. Okay, let's see. Let's erase some stuff so that we can do this math out. How many hydrogen atoms equals 1 mole of caffeine? Then we can say that for every 1 mole of caffeine, there are 6.022 times 10 to the 23 molecules of caffeine. And then we can say that for every 1 molecule of caffeine, we have 10 hydrogen atoms. All right, let's see what we get here. Take Avogadro's number, and we'll multiply it by 10. Absolutely get 6.022 times 10 to the 24 hydrogen atoms. Okay, so now let's look back at choice B, the one I very suspiciously skipped over. I should never erase that formula. So this says the empirical formula for caffeine is C8H10, O2, and 4. Remember that the empirical formula is the simplest formula, okay? So it's a formula that you should not be able to reduce by any variable. And we see here that each of these numbers is divisible by 2. That means that we can write a simplified version of this formula. If we divide all of these numbers by 2, we can rewrite this formula as C4, H5, O, N2. And this is the empirical formula. Okay. All right. Question number 49. Which of the following compounds are incorrectly named? Okay, so we're going to go through each one. The first one is FeCl3. The second one is HgCl2. SnS2 and KClO2. Okay, so it might be a good idea to just go through and try to name these as we would normally name them, and then see what we see when we compare it back to our choices. So right away, choice 1, we would hopefully see that what we have here is Fe3 plus and Cl minus 1. So if we were naming this, we were looking at iron 3. Chloride. Okay. If you refer back to the table of systematic versus common names that we've gone over before, you'll remember that iron 3 is the more positively charged of the 2 possible cations for iron. That means that the ending of iron would be the IC ending. So we could, instead of writing iron 3 chloride, we can call this ferric chloride. Okay. This matches the choice that is available, so this one's all right. We have HgCl2 here. So we see right away that this mercury that's here is Hg2 plus. Okay, so our possibilities for mercury are going to be a mercury with a positive 2 charge and a mercury with a positive 1 charge. So this is a positive 2 charge. So again, the thing that is more positively charged would have an IC ending. So this would be mercuric chloride or mercury 2 chloride. But it could not be mercurous chloride because that would indicate, or I should say this does not equal Hg plus. Okay, Hg plus 1 or just Hg plus, this is mercurous chloride. Okay, get rid of that so we have room for our next one. SnS2. All right, so now we have to break this down. We have 2 sulfurs and we have 1 tin. We know that every sulfur has a negative 2 charge, and we see that there are 2 of them. That means that the total contribution from sulfur has to be negative 4. If there's only 1 tin, that means that the tin charge has to be positive 4. that means that we're looking at the tin 4 ion here. Okay, it's attached to sulfur, so it would be tin 4 sulfide. And how is that one named here? Okay, they named it the IUPAC version. So yeah, tin 4 sulfide checks out. That's a good name. It would also be called stannic sulfide if we were going by that older naming convention, right? As opposed to, because that's stannic is the +4 ion. SN2 plus would be stannous. Okay, I'm going to erase that because I want a little more room for down here. You guys get to pause and rewind now, so it's great. And then finally we have this one. So we see that we have the potassium here, that's K+, and we have ClO2 -1. And we have to know the names of both of these things, right? So this is potassium, that's just potassium. You don't have to indicate anything special about it. It's always a +1 charge. So we don't even have to worry about putting the charge inside of a parentheses. We do have to be able to name this polyatomic ion, however. ClO2 -1 is the chlorite ion. So this would be potassium chlorite. So that is where your incorrect names come. Choice 2 is wrong and choice 4 is wrong. And that's why. All right. I'll let you do that word one by yourself. Okay, let's do number 51, because that's a really straightforward way to make sure that you are understanding the concept of molecular formulas. All right, so it's telling you here that butene has a simple formula or an empirical formula of CH2, and it has a molecular weight or a molar mass of 56 grams per mole. Okay, and it wants to know what the molecular formula of butene is. All right, so again, this is our empirical formula. So to find the molecular formula, we're going to have to do the empirical formula times n, right? And this will be the integer that we find by taking the molar mass and dividing it by the empirical formula mass. Okay, so, and that's, we're going to get that from up here. So we're going to take 12.01 plus 2 times 1.008. That's how we're going to get our empirical formula mass. And that's 14.026. Okay, so we're going to put that on the bottom here. And we're going to see what our n value is. And we get something that's very, very close to 4. Okay, so we're going to substitute 4 right there. So we're going to multiply each of the subscripts of the empirical formula by 4. And that's going to give us our molecular formula. So it's C4H8. Okay. Number 52, what is the percent by weight of sulfur in SO2? Some very straightforward problem again. But it's good to review those. So the percent by weight or the percent by mass for SO2 is going to be the mass of sulfur divided by the total mass of SO2 times 100. Okay, so I've got to look at the periodic table real quick. Sulfur 32.07, right? 32.07. Divided by right around 50%. Okay. Like I said, straightforward. It's good to review the straightforward ones, though. All right, we just did this one. Let's do number 54. I'm skipping over ones that we've done similar examples of, because there's just, we don't want to miss something because we were repeating the same thing over and over again. So for number 54, the number of atoms of oxygen. So how many oxygen atoms equals 27.7 grams of aluminum nitrate, AlNO3, 3. Okay. So first, we got to make a roadmap for ourselves, right? So we're going to get rid of the grams of aluminum nitrate, and we're going to convert it into moles. Okay, so we're going to get a molar mass value for that. All right, so we're going to do calculator things real quick. Okay, I got 213.01. Okay, all right, so now I'm gotten rid of my gram value for aluminum nitrate and I've converted it into moles. And now I want to make my transition from aluminum nitrate into oxygen atoms. So continuing along down here, now we're going to say in every 1 mole of AlNO3, there is 3. There are 9 moles of oxygen. Okay, because we're doing 3 times 3 there. All right, hopefully that's clear. Okay, so now we've gotten rid of moles of aluminum nitrate and we're in moles of oxygen. Now we want to go one more step because we want atoms. So in every 1 mole of oxygen, there's going to be Avogadro's number of oxygen atoms. Don't forget, when you see this right there, that's your key that you're going to have to use Avogadro's number somewhere, right? So we will do some math things. 9 times Avogadro's number. Okay, we get 7.05 times 10 to the 23. Oxygen atoms present in 27.7 grams of aluminum nitrate. All right. Oh, number 55 is a good one. I'll do that one. This one's kind of like working backwards from what we normally did. Okay, because this one's saying, well, what if we have 32 grams of oxygen? Like we know we have 32 grams of oxygen. How many grams of glucose would we have? You know what I'm saying? So we're going to start with this 32 number up here. We're going to start with 32 grams of oxygen in this case, and we're going to work backwards and get to the mass of glucose. All right, so same process that we had before. We're going to first convert grams into moles. Okay, and now we're going to look at our formula, which is C6H12O6. And we see that there are 6 moles of oxygen in every 1 mole of glucose. Okay, it's a 6-to-1 ratio. And we have to do, because we want a gram value here, so we're going to have to get a molar mass for this real quick. Okay. 180.156. So in every 1 mole of glucose, there's 180.156 grams of glucose. And that's how we get to our answer. So you see our grams of oxygen cancel out, our moles of oxygen cancel out, our moles of glucose cancel out, and we're left with grams of glucose. Okay. So let's see what that gives us. Okay, we get like 60.052. All right, now it looks like it's choice D, delta. Okay. Okay, just did that. Let's look at this one, number 58. It's a good thinking problem. Okay, what is the weight of one F2 molecule in grams? Okay, people love getting this question wrong because they're like, oh, F2? It's 19 plus 19. It's 38, no big deal. But you have to look at the question here. It's just 1 molecule of it, not 1 mole of molecules. Okay? So you have 1 F2 molecule. So now our periodic table is in grams per mole, so that's how we have to look at this in terms of. So So we know that they're going to be 6.022 times 10 to the 23 molecules of F2 in 1 mole of F2. And we know that in 1 mole of F2, double check on the exact mass of it, 18.998. Yeah, 37.996 grams. So 38 grams would be fine. My periodic table is just a little more detailed, I think, than other people's. So you see, we start out with 1 molecule, then we turn molecules of F2 into moles of F2, then we turn moles of F2 into grams of F2. Okay? Now we have to do our math stuff. And we see that 1 molecule of F2 is going to equal 6.31 times 10 to the negative 23 grams. See, it's an interesting thing because I feel like that's one where people look at it right away and they're like, oh, I know the answer to that. We should look at it a little bit harder. Let's scan through. Okay, let's look at number 63. 63, that's a good one. I mean, I think they're all good ones. That's why I put them on here. The number of atoms of oxygen. So how many oxygen atoms are in 27.7 grams of copper sulfate? So a lot like the other one. So hopefully this makes a lot more sense this time around. Okay. First, I have to get a molar mass for my copper sulfate. So I'm going to add that up real fast. 63.55 plus 32.67. 16 times 4. Okay, so the first thing I'm going to do is convert the grams of copper sulfate into moles. Okay. Then I am going to look at my actual formula for copper sulfate and see that in 1 mole of CuSO4, I have 4 moles of oxygen. Okay. And then every 1 mole of oxygen has Avogadro's number of atoms. So calculator stuff. I got 4.18 times 10 to the 23 oxygen atoms. And that's close enough to choice D for me to be happy. Okay, I want to look at the next one since we're here. The compound formed when 1.95 moles of oxygen combined with 1.46 moles of iron. Okay, so we have 1.46 moles of Fe, and we have 1.95 moles of oxygen. Now, right away when I look at this, my gut reaction is, well, how about I start by just following my empirical formula rules? Okay, I have these two mole values here. They're mole relationships between two elements that are in a compound. So what if I divide both mole values by the smaller of the two and see what their ratio is? Okay, and I get an Fe value of 1 and an oxygen value of 1.33. Hopefully by now, we're aware that when we see this decimal combination that we would take this entire simple formula or a pseudo formula and we would multiply it by 3 to get a whole number back out. So in that case, our formula is Fe3O4. All right, let's look at the next one. Okay. Tackle that one. Okay. So you're doing number 65 now. So we have a 1 gram sample of metal X combined with 0.22 grams of oxygen. And we know that overall the formula of the compound is XO2. Okay, and it wants to know what the atomic weight of just X is. So if you think back to the proportion stuff we did, we know that we can use the ratio that's present here to figure out what the ratio is here. Okay, like that, those are going to have a connection between the two of them. So we know that for every 1.00 grams of X, we are going to acquire 0.2200 grams of oxygen. We also know from our formula of the compound, it's XO2, that we're going to have 1 X atom for every 2 oxygens. And we know that 2 oxygens are 32.00 grams of oxygen. Okay, so now we've set up a proportion for ourselves. So we can use this relationship to figure out what the mass of X is on its own. Okay, so do my cross multiplication here. 32 equals 0.2200x divided by 0.2200. And I get like 145.5. And that would be the atomic mass of X. Okay. You guys can do that. You guys can do that. Ooh, so many word questions. Wow, let's look at number 73. That's a good question. Which of the following compounds contains the lead-2 ion? Okay, it's a question that could be really easy, but it also could throw you off. So you're just going to go through and you're going to look at each formula that's given and break it down into the ion portions of it, okay? So you have PbO, you have Pb2O, PbCl4, and Pb2S. Okay, so looking at these, okay, you start with what you know, okay, and the things in each of these cases that have the definite charge are the anions. Okay, so oxygen has a -2 charge. Chlorine has a -1 charge. Sulfur has a -2 charge. Right? Now the charge of the lead is going to be based on the charge of the anion and how many of them there are. So we only have one lead to balance out the charge of the oxygen here. So this lead has to be 2+. So right away, this is our lead 2. Over here, we have 2 leads for every 1 oxygen. That means each of these leads has to have a +1 charge for them to have a total charge of +2 and balance out here. In this case, there are 4 chlorines. There's only 1 lead. So that lead has to have a +4 charge so that it can balance out the total charge from the chlorine. Over here, this is similar to the option over here because sulfur's got a -2 charge and there are 2 leads here. Each lead has to have a +1 charge to have a total +2 to balance this out. Okay? That was number 73. What is the correct formula for potassium sulfite? Okay, this is a very straightforward question, and it's just asking you to know the formulas of polyatomic ions so that you can put together ionic compounds with polyatomic ions in them. When you are looking at any ionic compound and you want to find the formula of that compound, start by writing out the name, all right? Don't just try to guess this in your head, write out the name. And then underneath the name of each thing, write out the ion, including the charges. So we know that every potassium has a +1 charge. Hopefully you will know what sulfite is, SO3, and it has a -2 charge. Now once you have these written out and their charges included, now you can see the ratio that needs to exist between the two of them, right? So I'm going to need 2 potassiums to balance out the charge on this sulfite. That means that I have a K2 SO3 formula here. Okay? Just scanning through for some more. Yeah, we can do those. I'm going to go down to numbers 81, 82, and 83. Okay, those aren't hard, but it's good to review. So for 81, when naming acids, the prefix hydro is used when the name of the acid ends in. Okay. I mean, it's kind of a trick question. Hydro means that you have a binary acid, and all binary acids have an IC ending, right? An example of a binary acid is something like HCl. It's binary because there are 2 atoms that make it up. So the name of this would be hydro, and then you take the root of the anion, then you add the IC ending, and then you write acid. Okay? Number 82, what's the name of H2SO3? This is an example of an oxy acid. Okay, you can tell that because it starts with an H, so it means it's an acid, and there's an oxygen in it, right? So oxyacids are named based solely on their polyatomic ion. So you have to look at this and you have to say to yourself, I know that this is a sulfite. Okay, I know that's a sulfite ion. I know that if the polyatomic ion ends in ITE, that my oxy acid is going to end in OUS. And you're also going to know in this particular case that this is one of our two exceptions for oxyacids. So when I name it, I'm not going to take the root of this. I'm going to write sulfurous acid. Right, sulfurous acid and sulfuric acid are going to be our only two exceptions to that. And then number 83, we just answered by answering this question because it says when the name of the anion that is part of the acid ends in ITE, the acid name includes the suffix and it's OUS. Okay. All right, we can do some of these naming ones. Let's look at number 85. The correct name for the compound COCl2. So here you want to start by breaking these up into their ion forms, right? Hopefully you'll recognize right away that this is one of your metals that has a charge that changes depending on the compound. So we have to indicate the charge of that metal. We're going to find out what the charge of that metal is by looking at the charge of the anion that doesn't change, okay? We know that chlorine is always going to have a -1 charge. We know that there are two of them, so we know that it's going to have a total charge contribution of -2. That means that my cobalt over here has to have a +2 charge. And I also know that the charge attached to my metal, that's what goes inside the parentheses when I'm naming it, because I'm actually naming the charge attached to that metal. So this would be cobalt 2, and then I'll just name my anion per usual. Cobalt 2 chloride. Okay, number 86. What's the correct formula for barium chlorate? Okay, so now in this case, they're giving us a name. And again, you always want to start this by writing out the name because you want to be able to write the charges of each of the ions directly underneath the name. So I have my barium here, which is Ba2+. Barium's always Ba2+. Chlorate is a polyatomic ion, but you need to know. Okay, it's ClO3 -1. And now I can see the charge ratio between them. I know that I'm going to need 1 barium for every 2 chlorates because of the charge difference here. Okay, so I'm going to have 1 barium, and then I'm going to have parentheses around my chlorate, so I know that this subscript here applies to my whole parentheses. Ooh, and let's work through like 2 rows of number 90 real quick, okay? Just to make sure that we remember how to do this. Okay, so we're completing this table for calcium phosphate. Right, so right away you have to know what calcium phosphate is to be able to do this problem, right? So let's go through the process that we just went through for that last example that we did. We know that the calcium ion is Ca2+, phosphate is PO4, 3 minus. That means that the formula for calcium phosphate is going to be Ca3PO4 2. Right? I'll need 3 calciums for every 2 phosphates, and then they'll have an electrically neutral charge. I'll also need to know, to answer the questions that are in this problem, what the molar mass of calcium phosphate is. All right, so I'm going to do some calculator things real quick and find out the molar mass. Okay, I got 3. I will write that in blue. 310.18. Okay, and now I can answer these questions. Let's see, I will do the second row and I will do the fourth row. Okay. So row 2. And I want to fill in the blanks here. So I'm starting with 0.0992 moles of calcium phosphate. All right. So my first unknown are grams. How many grams are there in 0.0992 moles of calcium phosphate? Well, I know from my molar mass that every 1 mole of calcium phosphate has 310.18 grams. Okay. Get my calculator out. And that is 30.8 grams. Okay. Now I have 2 more blank spaces in this table. I want to know the number of molecules of calcium phosphate that are in 0.0992 moles. And I want to know the number of oxygen atoms in particular. Okay. So we'll start here with how many molecules equals 0.0992 moles. Well, I know from Avogadro's number that every 1 mole has 6.022 times 10 to the 23 molecules. Okay, so that means that there are 5.97 times 10 to the 22 molecules of calcium phosphate. Now I want to know in particular, well, how many oxygen atoms are in 0.0992 moles of calcium phosphate. I've already figured out that there are 5.97 times 10 to the 22 molecules in there. So if I know that, Ca3PO4 2. Then I can look at the calcium phosphate formula and I can say, well, in every 1 molecule of Ca3PO4 I've got 8 oxygen atoms. Okay, that means that in 5.97 times 10 to the 22 molecules of calcium phosphate, I have 4.98 times 10 to the 23 oxygen atoms. Okay. So we'll try one more and then we will call it a day. So we'll look at row 4. So this is a row we're working backwards, because in this case, we're starting with the number of oxygen atoms. Okay. So we have 3.13 times 10 to the 24 oxygen atoms. And now I kind of want to go in the reverse direction. So I want to go from oxygen atoms into my molecule of Ca3, PO4, 2. Okay? Because if I have this many oxygen atoms, right, and every one molecule of calcium phosphate has 8 oxygen atoms in it, now I can figure out how many molecules of calcium phosphate there are just by the number of oxygen atoms that I had in my calculation. So I take this number and divide it by 8, and then I get the number of molecules of calcium phosphate. 23. Okay. Once I have the number of molecules, now I can answer my next question. Well, how many moles of calcium phosphate is that? Well, I know that if I have 3.91 times 10 to the 23 molecules of calcium phosphate, I also know that there are 6.022 times 10 to the 23 molecules in 1 mole of calcium phosphate. Okay, so I take my molecules and I divide it by Avogadro's number, and that's going to tell me how many moles of calcium phosphate there are. Okay, now that I have that mole value, now we can calculate a gram value from it. So if I have 0.650 moles of calcium phosphate, I know from the molar mass that I already found that every 1 mole of calcium phosphate is 310.18 grams. Okay, so this is right around 202 grams of calcium phosphate. Okay, so hopefully that makes sense. I hope that this was a big enough selection of questions to get you through the review sheet. Obviously, if you have any questions, you should feel free to email me or Margaret Farmer. She will also answer any of your questions. Make sure that you get your camera, mic, all that stuff ready and working for your exam, and make sure that your Mastering Chemistry account is working. Those are the 2 things that we're going to need you to be logged in on and ready to use on Tuesday morning at 8 a.m. So I will see you guys then. I hope you have a good weekend. Hope you study hard. Yeah, and just let me know if you got any questions.